There's going to be another video later that goes through a more detailed circuit analysis, but right now I just wanted to show you how to start combining together parallel and series resistors. Now this is just like parallel and series capacitors, so if you understood that, you're probably fine here. But if we want to combine this entire thing together into one equivalent resistance, we have to identify the correct order to go in. So you see that there's a bunch of resistors, there's 4 of them, and if I just look at this, they're not all in parallel, they're not all in series. So you need to go step by step. So the first thing I'm going to do is combine this together into R1. I have 2 resistors that are parallel. And note that when I draw that circuit, I cut the wire in 2 places, so I can think about replacing that with 1 resistor. So I can then redraw the circuit replacing these 2 in parallel with R1. Now I look at my new circuit. I don't even need to look at this one anymore. I've redrawn it and I want to say, well, what do I replace next? Well, again, I don't have all 3 of these resistors either in series or in parallel. So I'm going to combine these 2 together. Note that again, I'm cutting the wire in 2 places and I can clearly see that these are in series. I'm going to call this R2, and note that if I wanted to calculate out the specific value of R1, I just use the equation for parallel resistance. Now I replace these 2 with R2, which I would calculate from the fact that these 2 were in series, so I just add those 2 resistances. And now I look at this final one and I go, they're in parallel. So I can combine this whole thing down to R3, where then I just have a single resistor, which is what you want to do. And in that case, R3 is then equal to finding these in parallel, so 1 over 25 ohms, and 1 over R2 to the -1. So that's how to go in this sort of process, and you are going to see some more complicated circuits, so it's good to be able to do this. Now, finding the value of R3 is sometimes something you're going to be asked to do, but frequently we're then going to be figuring out how much current or potential differences across the individual components. So this is really the starting point for more complicated calculations, which is why it's important to be able to do this. So instead of just plugging and chugging some numbers, let's make sure that we can understand conceptually what is happening. And I really like this question. So in this question, we're thinking about comparing the brightness before and after. So initially, we have our battery connected to bulbs A, B, and C, but this switch is open. So before, the switch is open, and we have A and B lit. Why? Well, we have one path for current. And so if we say how much current is passing through A and B, well, it's the same amount. So A equals B, where here we're referring to brightness. So that's the initial. What about after? Now the switch is closed, and we want to figure out how does the brightness on each of these bulbs compare to before? How do A, B, and C relate to one another? So we're closing our switch, which means that now we have current flowing this way, right? And we have current flowing this way. But that isn't necessarily to say that the current flowing in the smaller loop is the same. So in order to really understand this, we need to think about equivalent resistance. So what we can do is define each of these as if they were resistors with resistance R. So when we say these are identical light bulbs, that's what we mean. So before, our total circuit resistance was equal to 2R. Why? You had 2 light bulbs in series. Now what do we have? Well, if after I think about my scenario, I still have bulb A, but now I have this in parallel. So what does that become? That becomes one equivalent resistor, and I'm not going to do out the math explicitly, but this actually becomes R over 2. You have decreased resistance by having 2 bulbs in parallel, or 2 resistors in parallel. So what is our equivalent now then? Your total equivalent of the whole thing is going to be 3R over 2 because you're adding R to R plus half. So after our resistance has increased. What does that mean about our current? Well, we know that our EMF has stayed the same, so if our total equivalent resistance of our circuit has increased, our current has decreased. So this actually means that all of our bulbs are dimmer. Why are they dimmer or less bright? Because we've decreased the current coming out of the battery. So A initially, before, was brighter than it is after the switch is closed. B is going to be dimmer, not only because there's less current flowing out of the battery, but now there's actually a junction here. So initially C wasn't on. B and C are going to have the same brightness after the switch is closed, and they're each going to be dimmer than bulb A, since all of the current flows through bulb A, but here the current gets to split. So basically you have current I through bulb A, you have I over 2 through B, I over 2 through C. But since the current went down after the switch is closed, we know that A is dimmer too. So this is one way to think through it, and again, it's harder to do this without numbers. When working with components like light bulbs, as long as they're ohmic, which almost everything we talk about is, it's okay to assume a variable like R, but make sure that they're identical. If you're told that these are totally different light bulbs with completely different resistances, well, then you need to think through this a little more carefully. But as long as they're identical, you can simplify it down in this way.